Welcome back to the deep dive. Today, we're asking you to stretch your imagination a little. Forget about AIs that just recognize faces or, categorize images or even generate stunning artwork. Imagine instead an artificial intelligence that truly understands the world around it.
hmm
Not just what something is, but what it does, how it moves, and crucially, what might happen next.
Yeah, the predictive aspect is key.
Exactly. An AI that can predict future events and even plan its own actions in new, unfamiliar environments, much like a human does. That's the exciting, paradigm-shifting frontier we're exploring today.
It's truly a profound shift, I think. Think of it as the difference between an AI that can simply describe a video of a dog running across a field. There's a dog, it's moving fast, it's green grass. Pretty basic stuff.
Right. Descriptive.
And one that can predict where that dog will be in the next few seconds, anticipate its turns, maybe even guide a robot to safely interact with in that dynamic setting. This isn't just about passive perception. It's about moving toward proactive, intelligent interaction where the AI has an internal grasp of reality.
That's a fantastic distinction, and the system making waves in this space is a groundbreaking new AI from Meta called V-JEPA2 and its action condition sibling, V-JEPA2AC.
That's the one.
Our deep dive today will unpack how this system constructs a detailed world model from an enormous volume of raw visual data. We'll explore how that profound understanding then enables it to not only comprehend incredibly complex video, but also to directly control physical robots in the real world.
Yeah, and doing tasks it's never been explicitly trained for right out of the box. That's the really mind-bending part.
It really is.
Our main source for this deep dive is a seminal new research paper published just this month, so it's really hot off the presses, plus some accompanying insights from the research team and, honestly, some incredibly illustrative images that truly bring these concepts to life.
Yeah, those visuals are helpful.
They really are. This isn't just theory. It's about demonstrated tangible capabilities that are pushing the boundaries of what we thought was possible, maybe even just a year ago.
And as always, our mission is to cut through the, let's face it, often dense complexity of this bleeding edge research, extracting the most important nuggets of knowledge. We aim to give you that vital shortcut to being well informed about how AI is fundamentally learning to perceive, understand, and interact with our physical reality in ways that, well, increasingly mirror human cognition.
It's a fascinating journey.
So let's jump straight into the heart of it. To truly appreciate the significance of V-JEPA2, we first need to lay a foundational stone. What exactly is a world model in the context of AI, and why is it so indispensable? Why can't AI just, memorize facts or recognize patterns? Why this model thing?
It's a great question, and maybe the best way to grasp it is to think about how you, as a human, effortlessly navigate your day. You are constantly, almost imperceptibly, integrating low-level sensory inputs, what you see, what you hear, the tactile sensations you feel.
Right, it just happened.
Exactly. And you use all that to build an internal mental model of your immediate surroundings. But it isn't just about seeing. It's about intuitively understanding the underlying physics, the cause and effect, and the dynamic relationships between objects. You have an internal simulator running constantly, predicting what might happen next.
Right. So if I see a coffee cup perched precariously on the very edge of a table, my internal world model springs into action, like instantly. Without consciously thinking about it, I instantly predict that if I push it, it will likely tumble to the floor. Or if I carefully pick it up, the liquid inside might slosh, or it might feel warm. I don't need to have experienced that exact scenario 1,000 times to know what's going to happen. My brain generalizes, right? It applies a kind of intuitive physics.
Precisely. That's your world model working. This robust world model allows you to do several things that are fundamental to intelligence. It enables you to predict future states with remarkable accuracy, to deeply understand your present reality beyond just surface appearance, and most importantly, to plan goal-oriented actions effectively.
Deciding not to push the cup.
Exactly. Or how to pick it up carefully. Without this internal model, every single interaction you had would be a complete surprise, a constant stream of novel data points with no predictive power. Imagine if every time you reach for a door handle, you had to learn from scratch what would happen.
Chaos. Utterly exhausting.
It would be. And this concept, by the way, isn't new in science. It has deep roots in cognitive science. You can go back decades. Foundational theories from researchers like Craig back in 1967 talking about mental models, all the way up to folks like Friston in 2010 with his work on the free energy principle and predictive coding, basically emphasizing that our very perception is shaped by these internal predictive models. It's how we make sense of a noisy, chaotic world.
So, okay, if having a world model is so utterly fundamental to human-like intelligence, why has it been such an incredibly difficult, almost elusive challenge for artificial intelligence to replicate? What's been the bottleneck? Why haven't we had these robust AI world models for years?
Well, historically, building AI agents that can learn and utilize robust world models has been incredibly difficult. And it largely comes down to data, or rather the kind of data and how much you need. Many traditional AI approaches for learning behavior rely on explicit reward feedback or highly curated state action sequences. What that means is the AI needs to be told very explicitly, okay, in this situation, this was the right action, and here's the reward you get for doing it.
Like training a dog with treats for every correct move.
Pretty much. Imagine a robot learning to pick up a block. It performs the action, and then a human or a meticulously programmed system has to say, yes, you picked up the block successfully. Here's a reward point for every single attempt, every slight variation.
And the problem there is immediately obvious. Scalability, right? That sounds incredibly slow and expensive.
Hugely. Real-world interaction data is astonishingly limited compared to the vastness of human experience, or even just the amount of raw video out there. It's expensive to collect, and often, even when collected, it's insufficient for truly generalizable learning. If a robot has to perform an action tens of thousands, maybe millions of times, and get explicit labeled feedback for each attempt, well, it's just not practical for the sheer diversity of nuanced real-world tasks that humans do effortlessly.
Yeah, teaching a robot to make coffee that way would take centuries.
Exactly. And even when prior research attempted to leverage the vastness of internet video, which seems like an obvious source of observation-alone data, right? Just watch and learn.
Seems logical.
The focus often leaned towards building generative models, models that tried to predict visually perfect future frames. Now, generating a flawless video sequence is an impressive feat, technically.
Sure, we see those demos.
But it's also computationally very, very heavy. And crucially, it's not always the most efficient path to learning for planning. Predicting every single pixel, including all the chaotic, unpredictable noise like individual water droplets splashing, or the exact flutter of every leaf in the wind can actually be a distraction.
It's trying to predict too much. Stuff that doesn't matter for the core action.
Precisely. It can distract from learning the core predictable dynamics and causality of the scene. It's like trying to perfectly simulate every single atom in a storm, rather than understanding the overall weather patterns. You get bogged down in irrelevant detail.
Okay, so if traditional explicit feedback is too scarce and expensive, and pixel-perfect generative prediction is computationally prohibitive and maybe even inefficient for learning useful dynamics, how then does V-JEPA2 manage to tackle this fundamental challenge of building a world model? This is where the clever bit must come in.
This is truly where V-JEPA2 distinguishes itself and addresses that scalability problem head-on. It leverages what's known as a self-supervised hypothesis.
Self-supervised, okay.
What this means, in essence, is that the system learns about the world largely from observation alone. It doesn't need explicit labels, direct human supervision, or external rewards for every single piece of data it consumes.
Like a baby learning about gravity just by watching things fall.
That's a perfect analogy. The baby isn't getting points for correctly observing the apple falling. They infer the rules like gravity, how balls roll, how water flows from continuous unsupervised observation. V-JEPA2 works similarly, learning the underlying principles from sheer visual input.
So it's learning the underlying principles and dynamics from the sheer overwhelming volume of visual information available, like billions of YouTube videos, without someone having to sit down and meticulously label every single frame. That truly sounds like a game changer for practical, deployable AI. The potential for scalability is enormous.
It absolutely is, and it's a critical distinction. At its core, V-JEPA2 employs a specific type of architecture called a Joint Embedding Predictive Architecture, or JEPA.
JEPA.
Okay. This concept was actually introduced by Meta's chief AI scientist, LeCun, back in 2022, and it represents a fundamental departure from those traditional generative models we just talked about. Understanding this difference is really key to appreciating V-JEPA's breakthrough.
All right, let's unpack this JEPA thing a bit more because it sounds subtle but crucial. What's the fundamental difference between JEPA and, say, a typical generative AI model trying to predict the next video frame?
Okay, let's use that analogy again. Imagine you're watching that video of a dog running across a grassy field, like in the paper's figures. A traditional generative model trying to predict the next moment would typically aim to predict every single pixel in that future video frame.
Okay.
That includes predicting the precise location and angle of every single blade of grass, every tiny shadow, every individual hair on the dog maybe.
That sounds incredibly hard.
It is. It's incredibly complex, computationally intensive, and maybe even misguided, because it forces the model to try and predict things that are inherently unpredictable or just irrelevant noise, things that don't contribute to understanding the core dynamics of the scene, like predicting the exact shimmer on the water.
Right, the stuff that doesn't really matter for knowing the dog is running left.
Exactly. Now, JEPA, the architecture V-JEPA2 uses, operates differently. Instead of predicting every pixel in the raw input space, it learns by making predictions in a learned representation space.
Okay, representation space. What does that mean practically?
Think of this representation space as a kind of compressed, high-level understanding of the scene. It captures the important semantic information, the essence of what's going on, rather than the pixel-perfect details.
So with the running dog example.
With the running dog, JEPA is far less concerned with the exact orientation of every blade of grass. Instead, it focuses on the predictable aspects that truly matter for understanding. The trajectory of the dog, its overall motion, its shape changing as it runs, how it interacts with the ground, its general size and position relative to, say, a tree in the background.
So it learns what's important and likely to continue and ignores the random fluctuations.
Precisely. It effectively ignores unpredictable details, or what the researchers call noise, that aren't critical for understanding the core dynamics and causal relationships. It's looking for the meaningful patterns, the underlying structure of how things change, not every fleeting detail.
That makes so much intuitive sense. It's like learning the grammar of the visual world, the rules, rather than trying to memorize every single word and its exact pronunciation in every context.
That's a great way to put it.
And this selective focus on predictable information in this abstract representation space must be what allows it to learn so incredibly efficiently from massive, messy, uncurated data sets, right?
Yeah.
It's not getting bogged down in irrelevant minutia.
You've hit on the core insight, and it's why this is such a potential game changer. This selective focus allows V-JEPA2 to efficiently learn from truly vast amounts of internet-scale video. These are videos that just show sequences of states, things happening without direct observations of the actions being performed or explicit labels saying this is action X.
Just raw observation.
Just raw observation. This is a massive shift from older methods that required meticulously labeled interaction data, making the GP approach far more scalable and practical for real-world applications. The model simply observes, discerns the predictable elements of how the world changes, and builds its internal model from that.
Okay, so it's making predictions in this learned representation space, ignoring noise. But how does it actually do that? What's the clever mechanism under the hood that forces it to build this predictive understanding?
The system achieves this using a technique called a visual mask denoising objective. It sounds a bit technical, but the idea is quite intuitive.
Okay, lay it on me.
Imagine you're looking at a picture or a video frame, but a significant chunk of it is missing. Maybe a large square is blacked out in the middle, or diagonal section is hidden. The model is then given this incomplete information.
Right.
And its task is to fill in those masked parts. It has to infer what should be there based on the surrounding context, the parts it can see.
Like doing a really complex visual Sudoku or jigsaw puzzle.
Kind of, yeah. Our source material has some great illustrations of these masks. They show how they're constructed by sampling various overlapping blocks of different sizes, sometimes small 32 by 32 pixel areas, sometimes much larger 160 by 160 pixel blocks. The key is that the model learns to infer the hidden information within these masked areas.
And in doing so,
it isn't just memorizing pixels or textures. To predict what's hidden, especially across motion and video, it has to understand the underlying dynamics, the structure of the scene, how objects move and interact. It's essentially forced to learn the rules of the visual world to accurately complete the missing pieces, even when those pieces represent significant portions of the scene or long temporal gaps.
so by repeatedly being shown incomplete visual information, like a movie with scenes cut out, and having to predict what must have happened in those missing scenes based on what came before and after, it builds up an internal, robust understanding of how things move, how they deform, how they interact. And it does this all without being explicitly told what's happening or what actions are causing it.
That's exactly the idea. It's incredibly powerful, and it resonates with theories of how human brains might learn by constantly predicting and filling in gaps in our sensory input.
It's building up common sense about the physical world, visually.
Indeed. It's a remarkably effective and arguably biologically plausible way for an AI to build robust background knowledge, an intuitive understanding of how our physical world behaves. It's learning the fundamental grammar of visual reality, which is the foundation for predicting future states and, as we'll see, planning actions.
Now, here's where it gets even more interesting and, frankly, quite exciting for the field. The researchers didn't just propose this cool JEPA architecture for video, they then scaled it up massively.
Yes.
They systematically scaled various aspects of V-JEPA2's training, and they found this led to significant, consistent performance gains, really pushing the boundaries of what this self-supervised approach could achieve.
This is a critical point that can't be overstated. It's not just about a clever algorithm. It's about demonstrating that this fundamental approach works powerfully at scale, much like how large language models, transformed NLP by leveraging massive data and compute.
Right. Scale seems to unlock new capabilities.
Absolutely. The Meta team meticulously explored and optimized 4 key ingredients for the scaling. It wasn't just one thing.
And the first one, which always seems to be a key ingredient in modern AI breakthroughs, is data, massive data scaling. But you mentioned earlier there was a crucial twist, curation.
Absolutely. First, the sheer scale. V-JEPA was pre-trained on an unprecedented amount of data, a staggering 1 million hours of internet-scale video and 1 million images.
1 million hours. That's hard to even comprehend.
It's enormous volume, and just increasing the raw, uncurated dataset size they experimented with, from 2 million to 22 million videos, yielded a noticeable 1.0 point improvement in average accuracy on visual understanding tasks. So quantity helps.
Yep.
This benefit was particularly evident for appearance-based tasks, things like recognizing actions, scenes, objects in datasets like Kinetics 400, COIAN, ImageNet. The more diverse visual examples it saw, the better its general understanding.
But it wasn't just about throwing more and more raw data at it, was it? The strategic curation aspect seems incredibly important here. You hinted that not all data is created equal for this kind of learning.
You're absolutely right. It was vital. The researchers started with a truly massive, largely uncurated YouTube dataset known as YT1B, which is about 1.4 million video hours. Huge, messy, real-world collection.
Right, the fire hose.
Exactly. They then applied a sophisticated, automated, cluster-based retrieval process. This process carefully selected video scenes from that huge pool that aligned with the kinds of visual patterns and dynamics found in higher quality, more structured datasets like Kinetics, something V2, COIAN, and Epic Kitchens, which are often used for benchmarking specific AI capabilities.
So they were essentially taking that digital fire hose of YouTube video and intelligently filtering it, picking out the segments that were most relevant and representative of the kinds of understanding they wanted the AI to develop, like finding the signal in a vast amount of noise.
Precisely. And the results were stark. This careful curation, even when drawing from the same initial pool of raw data, led to a further plus 1.4 point average performance improvement over simply using the uncurated data.
Wow, just by being smarter about which data to use from the same source.
Exactly. It highlights a truly crucial insight for large-scale AI training. A well-chosen, representative dataset, even if smaller in raw volume, in this case, they ended up using 115 million curated scenes out of an initial 316 million raw scenes, can be significantly more impactful and efficient than simply throwing every bit of data at the model. Quality and relevance matter profoundly, not just sheer volume.
Fascinating. A powerful combination of both quantity and intelligent data quality. What else did they scale? What was the second ingredient?
Next up was scaling the model size itself. The neural network architecture. This also had a substantial and frankly predictable impact based on trends we've seen elsewhere.
Bigger models, more parameters.
Yep. Increasing the parameter count of the model's underlying neural network, they used a vision transformer, or VIT, from 300 million parameters, which is already a sizable model,
Definitely not small.
to a full 1 billion parameters, provided an additional 1.5 point gain in overall performance. This just reinforces the scaling laws we frequently observe across AI development generally. Bigger models, when properly trained with enough high-quality data and compute, often demonstrate bigger and more complex capabilities. It allows the model to capture more nuance.
We've certainly seen that play out dramatically in large language models. More parameters generally means the model can absorb and represent more complex patterns from the data. Makes sense. What was ingredient 3?
The third ingredient was simply extended training duration, letting the model learn for longer.
More time on task.
Exactly. The simple act of letting the model learn for longer, allowing it to process the vast data sets more times, more epochs, mattered significantly. Extending the training schedule from 90,000 steps or iterations to 252,000 iterations contributed another 0.8-point improvement in accuracy.
So just giving it more time to digest the data and refine its internal world model continues to yield benefits even at that scale.
It suggests that, yes, it's like repeated exposure and practice help solidify our own understanding of complex subjects.
That makes sense. And finally, the fourth scaling ingredient. You mentioned resolution and time.
Yes, that's the fourth piece, the fidelity of the input. They enhanced both the spatial resolution of the input frames, going from 256 by 256 pixels up to a higher 384 by 384 pixels, and significantly increased the temporal duration.
Meaning how long a video clip it looks at.
Exactly. Increasing the number of frames it processes in a sequence from a relatively short 16 frames up to 64 frames. They did this during both pre-training and evaluation. And this combined enhancement further boosted overall performance, contributing to that impressive final average accuracy of 88.2% they reported for the top model.
So higher definition pictures and longer movie clips help it learn better.
Essentially, yes. It demonstrates the model's ability to extract more nuanced and fine-grained information from higher fidelity visual inputs. It improves its understanding of subtle movements, textures, object details, and longer-range temporal dependencies that might be lost at lower resolutions or within shorter time windows.
So if I'm connecting the dots here, combining these four scaling ingredients, massive but carefully curated data, larger and more capable models, extended training periods, and higher resolution, longer temporal inputs, this whole package is what truly supercharged V-JEPA2. It created this incredibly potent system for understanding the visual world.
Absolutely. It's a comprehensive, systematic approach. It highlights that building powerful general-purpose AI often requires a confluence of these factors, working in synergy rather than just one single silver bullet. It's an impressive piece of engineering built on that strong JEPA theoretical foundation.
Okay, with those remarkable scaling breakthroughs making V-JEPA2 so capable, let's shift gears. Let's talk about what it can actually do. We know it understands the visual world deeply, but how was that measured? What are its concrete capabilities in terms of understanding and prediction?
Right, so V-JEPA2's general visual understanding was rigorously put to the test. They used a diverse suite of 6 distinct classification tasks. And these tasks were strategically chosen to provide a holistic assessment, looking at both the model's motion understanding capabilities and its appearance understanding.
Okay, so distinguishing between understanding how things move versus just what they look like.
Exactly. It's not just about recognizing a static object like cat or car. It's about understanding how things move and interact in dynamic environments, discerning running versus jumping or opening versus closing.
Got it. So how did it do on motion?
For motion understanding tasks, which are critically important for a world model, obviously they use data sets like something V2, diving 48, and gesture. These specifically require the AI to comprehend nuanced human gestures, actions, and object manipulations.
Things that unfold over time.
Precisely. And on these, V-JEPA2 demonstrated superior performance. It consistently outperformed other state-of-the-art visual encoders, highlighting its exceptional grasp of dynamic scenes and temporal relationships. This is where that self-supervised video pre-training really pays off.
Okay, so it's great at understanding motion. What about recognizing things based more on their static features, their appearance?
For appearance understanding tasks using benchmarks like Kinetics 400, Koyine, and the classic ImageNet, which involve recognizing actions, scenes, and objects more from their static features or general visual characteristics, V-JEPA2 proved to be highly competitive. It often matched or even surpassed other leading models trained in different ways.
So it's strong across the board, not sacrificing one for the other.
It seems to be building a remarkably robust and comprehensive understanding across both domains. And overall, the largest V-JEPA2 variant, that VIT-G3-4 model, the big one, trained on high-res, long clips, achieved that impressive 88.2% average accuracy across all 6 demanding tasks. That's a really strong result, a significant benchmark for this kind of general visual encoder.
Beyond just classifying what has happened or what's in a scene, one of the most compelling capabilities you mentioned earlier is its ability to anticipate future actions. This feels very close to how humans operate, doesn't it? We're constantly predicting what someone is about to do.
It absolutely is, and it's a direct consequence of learning a good world model, right?
Yeah.
If you understand how the world typically unfolds, you can predict the next likely step.
Makes sense.
They tested this using the Epic Kitchens 100 benchmark, EK100 for short. This dataset specifically involves predicting what a person is about to do next in a kitchen setting, like picking up a knife, opening a cupboard based on watching a video clip leading up to that action.
A very practical, everyday kind of prediction.
Exactly. And V-JEPA2 showed remarkable foresight here. What's particularly notable is that its performance on this anticipation task increased consistently with model size, again reinforcing those scaling laws we talked about. Bigger models were better predictors.
And there was a significant lead here compared to previous models, wasn't there? I remember reading about a big win.
A truly substantial one, yeah.
Yeah.
Despite using only 300 million parameters for this specific comparison, which is, relatively speaking, a more modest size for this level of performance. V-JEPA2 significantly outperformed a model called PlausiVL. PlausiVL was a previous state-of-the-art model, but it used a massive 8 billion parameters.
Whoa, 300 million versus 8 billion.
Right. And V-JEPA2 achieved a plus 12.1 points improvement on a key metric called action recall at 5. That corresponds to an astounding 44% relative improvement in predictive power.
That's a huge jump in foresight with a much, much smaller, more efficient model. That really speaks to the power of the JEPA approach itself, doesn't it?
It absolutely does. It suggests the way JEPA learns representations is fundamentally very effective for this kind of predictive task.
So it's not just better, it's remarkably more efficient in its prediction. What about the quality of those predictions? Even if it wasn't the absolute top guess, were the alternative predictions it made still reasonable? Did they make sense?
Yes, and that's a crucial detail that speaks to the depth of its understanding, not just getting the single right answer. Even when the model didn't get the exact top one prediction correct, its alternative suggestions were consistently highly coherent and plausible given the visual context.
Can you give an example?
Sure. The paper mentions that if the correct future action was, say, wash sink, the model might also suggest things like turn on water, or a clean wall nearby, or grab sponge, all of which are very reasonable, logically related alternatives in that kitchen scenario.
Right, they're all clustered around the same goal or activity.
Exactly. This isn't just random guessing. It shows a deep, nuanced understanding of the likely sequence of events and related actions in a dynamic environment. It's like it's grasping the script of how things usually happen in a kitchen. It understands the context.
Okay, this is really impressive visual understanding and prediction. So what does this all mean when we try to bridge the gap to language? Can V-JEPA2 actually talk about what it sees and predicts? Can we, ask it questions about a video?
Absolutely. And this is another really exciting area. Beyond just pure visual understanding benchmarks, V-JEPA2 can be effectively aligned with a large language model, an LLM, to perform open-ended video question answering, VidQA for short.
Okay.
This means you can pose questions in natural language about what's happening in a video. What object did the person pick up? Or why did they open the drawer? Or what are they likely to do next? And the combined AI system can answer them coherently and accurately.
That's truly incredible. But here's the part that really stands out. And it almost seems counterintuitive based on how a lot of multimodal AI has been developed. V-JEPA2 was pre-trained without any language supervision whatsoever.
That's correct. Zero language input during its main pre-training phase.
This goes against the grain, doesn't it? Conventional wisdom often suggested that visual encoders needed to be trained with massive data sets of image caption pairs, like CLAP-style training, to be good at these vision language tasks. How did V-JEPA2 manage to bridge that gap?
It's a profound testament, really, to the power and robustness of its purely self-supervised visual understanding. The hypothesis is that because V-JEPA2 learned such a deep, intuitive world model, purely from visual observation, understanding objects, actions, physics, dynamics, it built such a strong foundation that aligning it with language later was much more effective. It didn't need the language crutch during the core visual learning phase.
So the visual understanding was so good, it provided a better base for adding language later.
That seems to be the case. In controlled experiments, they took V-JEPA2, integrated it with a capable LLM like Qwen2-7b Instruct, and then fine-tuned it on a data set of image-video text pairs, about 18 million pairs, which is significant but not astronomical by today's standards.
And the results?
It exhibited competitive performance overall, but here's the crucial finding. It actually outperformed other powerful image encoders that had been explicitly trained with language supervision from the start, specifically on benchmarks focused on temporal understanding.
So tasks requiring understanding how things change over time in the video.
Exactly. Benchmarks like MVP, temporal bench, and TV bench. This strongly suggests that having a robust, self-supervised video encoder, one that truly understands dynamics and spatiotemporal reasoning, is perhaps more essential for these kinds of multimodal tasks than simply co-training vision and language together from day one. It learned the physics of the visual world so well that the language alignment became much easier and more effective, especially for temporal reasoning.
So it's not just about recognizing what something looks like, but fundamentally understanding how it moves, how it changes, and how actions unfold over time. That deeper dynamic understanding learned self-supervisingly from video seems to be the secret sauce.
That's what the evidence strongly suggests. And the results only got more impressive when they scaled up the language alignment data even further. When they increased the alignment data set to the full 88.5 million samples, a nearly 5x increase, and paired V-JEPA2, specifically the big VITG384 variant, with the powerful Llama 3.1 8B Instruct LLM.
Okay, scaling up both the vision model and the language alignment.
They achieved state-of-the-art results on multiple challenging VidQA benchmarks. These included Perception Test, MVP, Temp Compass, Temporal Bench, and Tomato. This really demonstrates the immense power and potential of combining large-scale self-supervised video learning with scaled language model alignment. It's a powerful validation of the whole approach.
V-JEPA2's ability to understand, predict, and even answer questions about the visual world is clearly incredibly impressive. But, for many of us, the ultimate test of a true world model is its ability to inform action. Can it move beyond observation and prediction to actually do things in the physical world?
Right.
This brings us to V-JEPA2AC, the action-conditioned version, and its direct, tangible application in robotics. This feels like the next frontier.
Here's where the rubber meets the road, quite literally, or maybe the gripper meets the object.
Yeah.
While V-JEPA2 excels at understanding and predicting, the next, and arguably most challenging step, is making that understanding useful for planning and controlling embodied agents, like robots. This is precisely what V-JEPA2AC, the action-conditioned variant, is designed to do. It's explicitly built to transition from passive observation to active, intelligent interaction with the physical environment.
So how do you take a model that's learned purely by watching videos and transform it into one that can actually decide what action to take and manipulate objects in the real world? What's the mechanism for bridging that gap from understanding to execution?
Okay, so it starts by taking the original, powerful, pre-trained V-JEPA2 model. Its core video encoder, the part that learned that deep understanding of visual dynamics from millions of hours of video, is then frozen after its initial training.
Frozen, meaning its parameters don't change anymore.
Exactly. It acts as a stable, highly perceptive eye for the robot, providing rich, consistent visual representations of the world based on its pre-training. Then, on top of this frozen encoder, a new component is added and trained. This new component is a 300 million parameter transformer network.
Okay, a separate module.
Right, and this new component is specifically designed to be an action-conditioned predictor. It learns to predict future states conditioned not just on the current visual input from the frozen encoder, but also on a hypothesized action the robot might take.
Okay, so it predicts if I see this and I do this action, then the world will look like that.
Essentially, yes, but predicting in that abstract representation space we talked about earlier, not raw pixels. Now here's the part that always makes me raise an eyebrow in amazement. How much real-world robot training data did it need for this new action-conditioned part? You'd imagine, given how complex and unpredictable real-world robotics can be, it would need thousands, maybe tens of thousands of hours of robot experience.
Yeah, my attempts at training even simple toy robots usually end in frustration and require tons of trial and error. This sounds hard.
This is truly where it becomes remarkable and honestly one of the most significant breakthroughs reported in this work. This action-conditioned training uses a surprisingly minimal amount of real-world robot interaction data. We're talking about just 62 hours of unlabeled video from a dataset called Droid.
62 hours. That's less than 2 standard work weeks. And unlabeled.
62 hours. Unlabeled. This data consists of short, typically 3-4 second clips of a Franka-Panda robot arm performing various tasks, but controlled by a human via teleoperation. And crucially, as you said, the data is entirely unlabeled. The model doesn't receive explicit rewards, no success or failure indicators, not even a description of what task was being performed.
So it just watched 62 hours of a robot moving around, doing stuff, without being told if it was good or bad, or even what it was trying to do.
Pretty much. It only uses the raw video stream coming from a camera watching the robot, and the robot's basic end effector state signals things like its position in 3D space and whether its gripper is open or closed. That's it. This is orders of magnitude less data than many traditional robot learning methods require, especially those needing explicit rewards or labeled demonstrations.
That's incredibly data efficient. So how does it manage to learn to predict actions and their outcomes from just raw, unlabeled video and basic robot state? It sounds almost like magic if it's not getting rewards.
It's not magic, but it's very clever learning design. The model is trained using a sophisticated combination of two types of loss functions, which are basically signals telling the model how wrong its predictions are. First, there's a teacher forcing loss. Here, given the current frame and the actual action the robot took in the data, it predicts the very next frame's representation. It's trying to mimic what it just saw happen, one step at a time.
Okay, learning the immediate consequence of an action.
Right. But maybe more importantly, it uses a rollout loss. This involves predicting not just one step ahead, but several steps into the future. And critically, it feeds its own predictions from earlier steps back as input for subsequent predictions.
Ah, so it has to learn to make predictions that are stable over time, not just for the very next instant.
Exactly. This forces it to learn a model that doesn't just drift off into nonsense after one or two steps. It helps reduce the accumulation of errors over longer sequences. This combination, the immediate prediction and the longer-term rollout prediction, helps the model learn the precise causal relationship between its hypothesized actions and the resulting visual changes in the environment. It's building a dynamic model of its own embodiment in the world. It's learning, in essence, if I do X, then Y will happen visually, and then Z will happen after that.
Okay, that makes sense. It's building an internal physics engine tuned to its own actions. So once V-JEPA2AC is trained in this way, how does it actually plan and control a robot to achieve a specific goal? Does it need explicit programming for each new task or environment? Or can it generalize?
No explicit programming per task, and this is where its zero-shot planning capability truly shines. Once trained on that relatively small 62-hour data set, V-JEPA2AC becomes this powerful, latent world model capable of zero-shot planning.
Zero-shot meaning it can do tasks it wasn't specifically trained on.
Exactly. Here's how it works. You give it a goal image. For example, in an image showing a cup moved to a new location on a table, maybe like we see in those illustrations in the paper. The robot doesn't get step-by-step instructions on how to move the cup. Right. Instead, it needs to figure out the optimal sequence of actions to get its environment from the current state to that desired goal state represented by the image. V-JEPA2AC does this by minimizing something called a goal-conditioned energy function.
Okay, energy function.
You can think of it like this. The robot essentially imagines or simulates internally, using its learned world model, many different possible short sequences of actions it could take. For each imagined sequence, it predicts what the future visual state would look like in that abstract representation space. Then it picks the action sequence that leads to a future state that is predicted to be closest or most similar to the desired goal image's representation.
So it's like the robot is running incredibly fast internal simulations. If I move left, does it look more like the goal? If I move forward and close my gripper, does that get me closer? Finds the best short-term path?
Exactly. It finds the best initial action or short sequence based on these internal simulations, and then it executes that first action in the real world.
And then, does it just follow the whole imagined sequence?
No. And this is key for robustness. It executes the first action, then it looks again at the world through its camera, gets the new current state, and then it replans from there. This iterative process is a form of model predictive control, or MPC. Plan a bit, act, observe, replan. This allows it to constantly correct for errors and adapt to unexpected changes in the environment.
That makes it much more robust to the real world's unpredictability.
Precisely. And what's even more impressive, highlighting the model's generalization, is that these V-JEPA2AC models were deployed zero-shot on real Franca Imica Panda robot arms in two completely different labs that were not part of the original 62-hour training dataset collection.
Wow, so new environments, potentially different lighting, different backgrounds.
Exactly. And they operated using uncalibrated, low-resolution monocular RGB cameras. Just a single regular camera view, no fancy depth sensors, or multiple carefully calibrated cameras. This demonstrates a remarkable level of generalization to new environments and camera setups. This isn't just a carefully controlled lab trick. It's a significant step towards truly robust, adaptable, real-world performance.
That truly is the holy grail for robotics, isn't it? Generalization without needing massive amounts of retraining for every new situation. It unlocks so many possibilities. Let's dive into some of the specific robot manipulation examples it successfully handled. What kind of dexterity and problem-solving did it demonstrate in these new labs?
Certainly. One foundational task they tested was single goal reaching. Here, the robot was simply tasked with moving its end effector, essentially, its gripper to a desired location in 3D space, specified only by showing it a goal image with the gripper in the target position.
Okay, basic pointing or moving to a spot task.
Right. V-JEPA2AC consistently moved the end effector to within less than 4 centimeters of its target location, just based on that single image. Now, this might sound simple, but achieving this precision using only visual feedback from an uncalibrated camera is actually quite challenging. It's akin to visual servoing, a classic robotics technique, but here it was learned entirely from that unlabeled real-world data, rather than relying on classical approaches that require painstaking geometric calibration.
Impressive precision from vision alone.
Yeah, and interestingly, they observed that the model's internal energy landscape for planning that sort of mental map it uses to find the best actions was remarkably smooth and convex. This means it's easy for the planning algorithm to find the right direction to move. It doesn't get stuck in lots of bad local optima, which helps make the planning effective and efficient.
That's a good foundational skill, showing it understands its own body and space relative to its visual input. But what about more complex interactions, like actually grasping and moving objects? That adds a whole new layer of complexity dealing with physics and contact.
Absolutely. That's where prehensile manipulation comes in. This involves more intricate tasks, like accurately grasping an object, reaching to a target location while holding an object, and the classic pick-and-place operation: grasp, lift, move, release.
The bread and butter of many robotic applications.
Exactly. These are significantly more complex because they involve interacting with objects that have varying shapes, weights, friction properties, and so on. For the pick-and-place task, the model demonstrated remarkable multi-stage goal handling. It could figure out how to first approach and grasp an object accurately, then lift it and move it towards a target location, and finally place it down precisely.
And manage the sequence automatically.
Yes, it automatically switched between these sub-goals: grasp, move, place, which is a very human-like ability. It shows a higher-level understanding of the overall task structure, not just reacting moment to moment. The source images in the paper beautifully show examples of the robot executing these composite skills fluidly with things like cups and boxes.
That's really cool. And how did it perform on these truly challenging tasks compared to other cutting-edge models they tested against? Was it just okay, or did it excel?
It was more than competitive. V-JEPA2AC achieved the highest success rates across these challenging manipulation tasks compared to the other state-of-the-art models they included in their comparison.
Really? Highest success?
Yes. For instance, in one of the test labs, it had a remarkable 100% success rate on the basic reach task, meaning it consistently moved its gripper to the target object accurately. Across both labs it was tested in, it averaged around 65% success for grasping objects and about 25% success for the full pick-and-place sequence.
Okay, 65% and 25% might not sound perfect, but for zero-shot pick-and-place in new environments with uncalibrated cameras, that's actually pretty strong, isn't it? Especially compared to others.
It's a very strong performance for this setup. The variation in success rate, particularly for pick-and-place, depending on the specific object type, like a small box versus a larger cup, and the initial conditions, really highlights the inherent challenges of manipulating diverse objects in the real world. But its overall performance was groundbreaking for a zero-shot system learned with so little interaction data. It showed strong capabilities on object interaction, even with varied objects.
That's truly very impressive, especially considering that minimal 62 hours of training data for the action part. But, in practical robotics, especially in industrial settings or maybe even domestic ones someday, speed and efficiency are absolutely paramount. How fast can V-JEPA2AC actually plan and execute these actions compared to other approaches? This seems crucial for real-world deployment.
This is indeed a critical point, and it turns out to be a key performance advantage for V-JEPA2AC. It's where it really pulls ahead of some alternative methods. One of the most compelling findings in the paper compares V-JEPA2AC's planning efficiency to other action condition video generation models, like a model called Cosmos, which uses a latent diffusion model for its predictions. Diffusion models are powerful, but often slow.
Okay, how do they compare on speed?
For planning just a single action, V-JEPA2AC required only about 16 seconds on average to formulate a robust plan. And that includes using 10 times more samples during planning than the minimum needed just to make the plan extra reliable and less prone to errors.
16 seconds per action.
Okay.
And Cosmos?
Cosmos, the diffusion-based model, took a staggering 4 minutes to plan a single action.
4 minutes for one small movement. That's an eternity in robotics. That would mean a full pick-and-place sequence, which involves maybe 50 or 100 small actions.
It could take over an hour, easily.
Yeah.
It's simply not practical for almost any real-world application where things need to happen in a reasonable time frame.
Absolutely. A robot taking an hour to move a cup across a table isn't very useful.
You're exactly right. That full pick-and-place trajectory that would take ages with a model like Cosmos can be performed significantly faster, much more practically, with V-JEPA2AC, because its planning loop is so much quicker. This efficiency is paramount for robots operating in dynamic environments, whether it's a factory assembly line needing to keep pace, a warehouse robot picking items quickly, or eventually an assistive robot helping in our homes.
So the ability to plan quickly means the robot can react faster to changes, correct errors faster, and just generally perform tasks in a timely, useful manner.
Exactly. This speed isn't just a benchmark number. It's what makes these advanced world model-based capabilities potentially usable outside of a research lab environment. It crosses a threshold of practicality.
So V-JEPA 2AC is powerful, data efficient, generalizable, and fast at planning. It sounds amazing, but are there any significant limitations or challenges that still need to be addressed as this technology continues to evolve?
Every breakthrough has its boundaries, right? At least for now. Yes, certainly. There are a couple of important limitations to keep in mind, and the researchers are quite transparent about them in the paper. First, there's something they call camera positioning sensitivity.
Okay, what's that?
Remember how the model learns implicitly how the robot's movements relate to the visual scene, just from that single uncalibrated camera?
Yeah, without being told the geometry.
Right. Well, because it's inferring this relationship, its performance can be quite sensitive to exactly where that camera is positioned relative to the robot's workspace. The researchers noted they had to manually find good camera placements for their experiments. For example, if the robot's base isn't sufficiently visible in the camera view, the model might struggle to correctly infer the action coordinate axis, which could lead to planning errors.
Okay. So while it generalizes well to new environments overall, the specific viewpoint of the camera within that environment still needs some careful consideration for optimal performance. It's not yet at the point where you can just plop a camera down absolutely anywhere and expect it to work perfectly.
Exactly. That implicit inference has its limits based on the available visual information. The second key limitation they mention is related to long horizon planning.
Meaning planning very far into the future.
Yes. Like many autoregressive prediction models, models that make predictions step by step based on their previous predictions, V-JEPA2AC can experience error accumulation over very long planning horizons.
The errors build up over time.
Potentially, yes. If a task required an extremely long, intricate sequence of actions, maybe hundreds of distinct steps without intermediate feedback or replanning the compounded errors from those internal simulations might make the very long-term plan unreliable. The predictions could drift further and further from reality.
So it's better at shorter-term reactive planning.
It's exactly. For the kinds of tasks they evaluated, which typically involve shorter sequences where the robot replans frequently using that model predictive control loop we talked about, replanning every few seconds, a short planning horizon proved entirely sufficient. It manages well by constantly correcting course based on new observations. So for these quick adaptive tasks, it's excellent. But for tasks requiring, say, planning a complex multi-hour assembly process perfectly from the start without feedback, it would likely still face challenges.
Those limitations seem understandable given the sheer complexity of the problem, but honestly, even with those caveats, these results feel like truly incredible leaps forward in AI and robotics. It's moving beyond just pattern recognition into something much deeper. So what does this all mean for you listening in? Whether you're a researcher, an engineer, a developer, or maybe just someone fascinated by the accelerating future of artificial intelligence. This deep dive into V-JEPA2 and V-JEPA2AC, well, it really represents a profound step forward, doesn't it?
I think so.
It unequivocally demonstrates that AI can learn an internal, predictive world model from mere observation alone by watching billions of, unlabeled, uncurated videos, much like a child simply observes the world around them.
Yeah, learning the implicit rules.
And crucially, it shows that AI can then leverage that deep understanding to skillfully interact with the physical world, performing complex robot manipulation tasks it has never seen before in that specific environment, and doing it with remarkable efficiency.
The power of self-supervised learning, particularly through these robust architectures like JEPA that focus on prediction and representation space, is truly transformative. It directly addresses that fundamental scalability problem of AI by allowing it to learn useful things from these vast unstructured data sets that we just couldn't leverage effectively before. And this opens the door for robots and other AI systems to acquire a deep, perhaps even intuitive understanding of physics, causality, and dynamic relationships. That kind of understanding is absolutely crucial for real-world adaptability and intelligence. This isn't just about making robots perform specific, pre-programmed tasks slightly better. It feels like a foundational step towards truly intelligent, adaptable machines that can learn and function in the unpredictable complexity of our physical reality.
Absolutely. Now, for our final provocative thought for you to ponder as we wrap up. The researchers successfully scaled V-JEPA2 up to 1 billion parameters in this work, and they showed consistent performance improvements with each scaling step. But as we know from other areas of AI, particularly vision models, prior research has shown that these kinds of vision encoders can potentially go much, much larger. Think 20 billion parameters, maybe even more in the future.
Right, the scaling might not stop at 1 billion.
So think about that for a moment. Imagine what an even more expansive and even more incredibly detailed world model learned entirely from even vaster observations of the world could enable.
What capabilities might emerge from a 20 billion parameter V-JEPA, or something like it, trained on perhaps trillions of video frames?
Exactly. How might this shape the future of robotics in our homes, our factories, our hospitals, construction sites, everywhere? If AI can genuinely learn and adapt to virtually any physical task with unprecedented speed and efficiency simply by observing the world and maybe a tiny bit of interaction, what new industries, what new capabilities, what new forms of human-robot collaboration might emerge?
The potential is truly staggering. It really does hint at a future where robots aren't just pre-programmed tools executing fixed routines, but perhaps truly intelligent, adaptable partners in our physical world. Learning on the fly, understanding context, predicting outcomes, it changes everything.
The possibilities feel truly boundless. Thanks for diving deep with us today on The Deep Dive.